next speaker is one of our NIAC fellows who could not make the trip because of what happened with NIAC. Lynn Rothschild with NASA, I believe NASA Ames, if I got that right. Lynn is actually appearing by video as pre-recorded, but she will be doing the Q&A in real time after the video plays. So hit it.
Today, I'd like to introduce a radically different approach for human exploration. Now, as we go forth from planet Earth, humans take their needs with them. Human needs include transportation, life support, importantly food, oxygen, medicine, waste recycling, clothing, and so on. They need habitats to protect themselves. They need power, heat, and light. They need radiation protection, which becomes increasingly important away from Earth's cocoon. Communication systems, of course, Cassia, you're not going to get there at all. But we have challenges. One of the big challenges is upmass. Anything that you have to launch against Earth's gravity is expensive, and it means that something else won't be able to come. So it's a zero-sum game. So as I mentioned, this is tied in with cost, which of course is extremely high. You also need to worry about storage, reliability, and flexibility. You can't go off planet, particularly on a long duration mission, and say, oops, I forgot. You certainly need power, and you end up with a self-sustainability. Something I've argued to my colleagues means that we at NASA create the ultimate circular economy. Now, here is a black box, and I'm going to tell you what's in the black box. It's something that's going to solve these problems. It's programmable, it's modular, it's self-replicating. Whoa, now you're getting much more interesting than your average computer, and it's self-repairing, which is well beyond what a computer can do today. It has the ability for advanced chemical synthesis, including making polymers with exquisite precision. It can sense as little as a single molecule, even when dormant. It can do precise mineral extraction. Some of them have built-in solar cells. It can be dormant with minimal energy input. It doesn't need any petrochemical or electrical input. It has the ability for atomic scale precision assembly. It's evolvable. And Earth's hardware store has over 10 million variants on its shelves today. So what is in this black box? I'm sure you've guessed it. It's life itself. And once we start thinking of life as a technology, it is incredible what we can do. And if you add to it synthetic biology, the design and construction of new biological functions and systems not found in nature, you can do unbelievable amount. As we don't say at NASA, the sky's the limit, because it isn't. And probably that's as good a description of synthetic biology as any. So I'd like to give you some big ideas for the rest of this talk. The first is that we're going to use organisms for material production off planet. Now, we certainly do that on planet Earth. We've done that throughout human history, whether it's using the wool from sheep for clothing or leather, or taking trees and chopping them down and building houses. But we're not going to take sheep with us, or trees, or cotton plants, and probably not spiders or silkworms either, although I suppose possible. We are going to take these. These are bacteria. This particular bacterium is Bacillus subtilis, which is a spore former. So those white dots you see in this micrograph that I took are the Bacillus subtilis spores. I am very bullish on these particular organisms because they've been proven to be able to withstand the rigors of space for nearly 6 years on the LDEF mission. So what if you take these spores and you engineer them to produce silk or wool or cellulose or to bind metals or whatever? And that is our first big idea. How could we apply this? Well, let's start with habitats off planet. Now, the traditional approach is much like a turtle. You bring your habitat with you. So here the Apollo astronauts looking at their home while on the surface, and this in case it was the lunar module. The ISS astronauts, of course, live in ISS. New approaches include robotic construction of regolith or ice houses, but we believe that there is an even better way. And that is to use biology as technology and use mycotecture off-planet, something that is currently being funded by NIAC Phase 2. Here is the image that Chris Maurer, my partner in crime, the principal architect at Red House Studio, imagines of what it's going to look like on the surface of the moon or Mars. So these structures are built with fungal mycelia. What are fungal mycelia, you may ask? Well, here is a mushroom. Everyone's familiar with mushrooms, but that's the fruiting body of a multicellular fungus. The main part of the body is composed of these thread-like structures called mycelia, mycelium singular, mycelia plural. Here's a micrograph I took of fungal mycelia. Now, it turns out that you can use these mycelia as a binding material, say binding wood chips, to make imitation particle board. Or you can use the mycelia themselves to make imitation leather. And so this has led to a field called mycotecture, something that's being explored on Earth because it's low mass, inexpensive, it's a great material, flame retardant, adaptable to building at site, and potentially self-healing. It's sustainable, compostable, and can be used for multiple things besides buildings themselves, tables, chairs, and so on. And many of these arguments for using mycotecture on planet Earth would also apply to using mycotecture off planet. So again, here is the vision that we have, thanks to Chris's beautiful rendition. And here's some of the things that we have already done in my lab. We have the fungal mycelium on the left growing on lunar Regulus simulant, Martian Regulus simulant, with just the addition of some nutrient solution. And you can see on the right a stool built from using mycotecture that the students in my lab on the iGEM team made a few years ago. It only took about 2 weeks, including post-processing, for them to make the stool, which you can see created a very strong structure rated for the average Stanford student. So now that we're no longer limited by form factor, why not add bioprinting? Now, it turns out that biomaterials often rely on hierarchical structures. So when you look at a bird, even the feather of a bird, it's not a homogeneous substance. It's got all sorts of structures starting at the molecular level from the keratin monomers all the way through the next hierarchy, the nanostructure, where you have keratin filaments, then layered materials, and the macrostructure is the vein or the feather itself. So imagine using this approach where you bioprint bacteria, for example, that have been engineered to make the components of bone, and then you print bone and you end up with incredible structure. Maybe you're back to the future here. So our grand vision is that you use the sunlight to power photosynthesis, which then allows you to create all sorts of biological compounds that you then feed to a production organism, for example, a Bacillus subtilis that has been engineered to make nanocellulose, so an imitation of a cotton or wool or whatever, something that then could be used as the inputs for bioprinting, again, funded by the NIAC program. And you've now able to print whether it's an advanced composite or some kind of cool material that you use for clothing, or even a stake in space. Or medical devices or whatever. Here's another big idea for you, and that is that we will send digital information to make DNA. Now, up to very recently, if you wanted to make DNA, you had an organism that made it, and it had absolute physical continuity with the origin of life. But that's no longer true. Our students make up sequences in silico on their computers. They hit send to a DNA synthesis company, and the DNA synthesis company reads this information and takes it and makes the actual physical instantiation of the DNA. Now, my point is that it really doesn't matter whether this DNA synthesis company is across the hall from you or on a different planet or even a different solar system. The point is that we have now broken that physical link. Here's another idea for you. Biology does chemistry on the Earth, and it has throughout human history for us. Why not beyond Earth? And I think this picture pretty much sums it up for a Saturday talk. We will rely on nanotechnology just the way we do on the Earth, but much of nanotechnology involves having very large clean rooms and so on for synthesis. Not so if you're a cell. For example, the production of DNA involves incredibly precise nanotechnology. You have one amino acid wrong in a chain of proteins, you could end up with sickle cell anemia or who knows what. So the pressure to have absolute fidelity in DNA synthesis as well as protein synthesis is there. Now, we've harnessed that capability thanks to most of the work of Simon Vecchione, who started with me when he was a senior at Brown on an iGEM team in 2013 and is now a postdoc at NYU in New York. He has taken DNA and used that as a scaffold to create a wire. Now, it turns out DNA, the double helix, can be forced to have a mismatch, so two cytosines are across from each other rather than cytosine binding to guanine. And when you have that cytosine-cytosine mismatch, you can incorporate an atom of silver with absolute precision. Turns out, actually, with the thymine-thymine mismatch, you can incorporate mercury. So using this big idea, you can not only make a wire 1 atom in thickness, but you now have a way to extract metals. And this is something that we proposed and were funded by the NIAC program several years ago, and that is to take an integrated circuit, grind it, and use biological approaches to extract the metals and then reprint an integrated circuit. Now, we've talked about DNA and metal binding, but it turns out that, say, roughly 50% of the proteins in our body can also bind metals. I often tell people, if you want to know what metals we use as humans, go look at the back of a vitamin bottle. But it turns out they're not only the naturally occurring peptides, but they're also ones that have been designed to bind metals. A very common one in use in labs today is using a hist tag. So these are several histidine amino acids in a row, and they can then bind nickel, zinc, and cobalt. We've taken this capability, combined that with our mycotexture work by putting peptides on the surface of fungal mycelia that would bind copper, and then created a copper filter. We've published this, and we are now currently waiting on a patent. Here's another big idea. It's not just the electric eel that converts chemical energy into electrical energy. Every one of us does that every day. Presumably we're not eating to grow at our age, we're eating to do things like metabolize, and that includes making electricity. So in principle, that could be harnessed, but also why not create life 1.5, something my students have called the hell cell. So you take the capability of organisms that perhaps live at very high temperatures or low pH or whatever, and put those into other cells to allow them to have these capabilities. Or maybe life 2.0, life de novo. And there's a group of us under the rubric of an NSF research consortium network called the Build-A-Cell Network in the United States working on that. But there are also many international colleagues working on this whole idea of a bottom-up approach where the components of the cell are put together and with an attempt to make a living cell that can do all sorts of various things. Now, humans have needs, as I've mentioned many times, including for pharmaceuticals. And as NASA plans the Artemis missions to the moon and beyond, what happens when an astronaut gets sick? It's one thing when you have a short Apollo mission and you've carefully screened the astronauts, or they're on ISS and can come home. But what happens if you're moving on with no possibility for resupply? Well, astronauts currently bring in a very extensive list into space of medications. Now, the problem with bringing all these is you have an upmass issue. But even more important, you cannot predict the exact needs of the astronauts. You have the potential to run out of any given medication. But the real killer here is that some of them, particularly this new class of compounds called biologics, have a very limited shelf life of about 6 months. And so if you're talking about 2.5-year round trip to Mars, or certainly a much longer mission if you're going outside of our solar system, you simply have to make medications on site. So with this push towards long duration missions, you cannot do this carry everything approach. So we have proposed an astropharmacy, again funded by the NIAC program with a wonderful international team of collaborators. And what we've proposed to do is, once again, to program Bacillus subtilis to make some of these pharmaceuticals and then have them produced in space, do simple purification steps, and have them ready for the astronauts. Now, it's time to test many of these ideas in space. So most of what I've showed you, we have proof of concepts with my lab or people affiliated with my lab. But many of these things have not been tested, and we were very fortunate a few years ago to be selected to have a secondary payload on the DLR EuCROPIS mission, Euglena crops in space. And what was particularly cool about this satellite is that it spun at 3 different speeds to mimic microgravity, lunar, and Martian gravity. And on this mission, we were able to test some of these very basic synthetic biology approaches, something we will talk about on another day. So in summary, we've talked about biology as a technology, and particularly synthetic biology and its use for exploration, particularly for in situ resource utilization, but in general to solve this upmass issue, including on-demand drugs, making habitats or other structures off-planet, recycling metals, and so on. There are also scientific goals that we can use synthetic biology for, including making exploration platforms. We made a little biodegradable drone a few years ago, or astrobiology itself to understand the origin of life, the limits to life, the what-if questions, and more recently, aeronautics, looking at green aviation, biofuels, and so on. But this may include novel materials and so on that are useful off-planet, and now we're now looking at aeronautics off-planet. And so with that, I thank you very much for your attention. Ad Astra to the stars.
Thanks, Lynn. And with luck, you're on Zoom and able to join us real time, I hope.
I am. I'm here.
There we go. Great.
I'm sorry. I'm not with you. I do apologize for not being with you. But I did think that the best thing was pre-recorded, because even though I live above Silicon Valley, our internet connection is not the best. So I do apologize, but I'd be happy to take questions for however long I have.
Great. We've got a couple of minutes. So Dennis?
Okay, great. So here's certainly a down-to-earth question. Does the binding of metals to fungal mycelia proteins in the human gut possibly account for leaky gut syndrome?
Oh, wow. I never thought of that. But actually, I just want to clarify that what we were doing was putting engineered peptides on the surface of fungal mycelia that we knew specifically would bind copper. It is true that there are some peptides on fungi that I believe can bind metals, and it's been suggested that some can be used naturally as a sop. So I don't know what effect that might have, or whether those proteins would normally be digested before you even got to your intestine or not. So it's an interesting question. I'll follow through on it, but I suspect you don't need to give up mushrooms.
Thank you. Here's another question. In de novo synthesis, do you plan to design cells from scratch or to remove the DNA from specific cells as quote unquote target organisms?
Again, fabulous question. I'm not doing a lot of that myself, but I went through this very quickly. What the question is describing is what's known as a top-down approach, which is something that, for example, the Venture Institute has worked on in Southern California, where you start to remove bits and pieces of cells, or you take out a whole nucleus and do a transplant. What many of the people in the community that I'm involved with that build a cell are doing a bottom-up approach, where they're making lipid vesicles and stuffing things into it. Lipid vesicles themselves are really easy to make abiotically. It's the old, shaking up a bottle of salad dressing with oil and vinegar, and you've got your little vesicles. And then it's a matter of putting things in. Some of it you can put in by having the DNA or whatever in the aqueous phase. Then you start to get a little bit more complicated, actually having the synthesis of proteins and so on, which you can do briefly, having those then inserted into cell membranes all the way to getting structural components in and having cells divide. But there's been a seminar series on Mondays where people around the world have given talks that it knocks my socks off every week. There is an amazing talk, and it makes me very confident that we're getting very close to having the different components of what a cell does being created artificially. Now, these may, in some cases, be very similar to what we already use and has evolved. Sometimes it's sort of a workaround, but again, the unbelievable work being done by my colleagues that will hit the front page of every paper at some point soon, I would imagine.
Wonderful. Thank you so much, Lynn.
Lynn, thanks very much. We appreciate it. That's
Thank
our time
you.
limit. And thanks for appearing live with us. And we want to see you in person in 2023. Thanks.
Oh, gosh, I want to be there. Thank you. Bye.